In lesson 3.2, we're going to build the unit circle. The unit circle is an extremely powerful tool, and all of the work that we've been doing so far has led up to being able to develop this unit circle, which we will then be able to apply to many different situations. First, we should recall that we defined trigonometry on a point on the coordinate plane, for example, x comma y, by drawing an angle in standard position whose terminal side goes through the point x comma y. From x comma y, we would drop an altitude to the x-axis, and the angle theta would be measured by the angle in standard position. This makes it such that the hypotenuse, that is not the hypotenuse. The hypotenuse is defined from the origin to the point. The opposite ends up being the y-coordinate, and the adjacent ends up being the x-coordinate. And so in quadrant 1, both x and y are positive, meaning that our sine ratio, sine of our angle theta, will produce a positive ratio. Cosine theta will produce a positive ratio, and tangent theta will also be positive. And this is consistent with our definition of trigonometry as far as geometry went. What being on the coordinate plane allows us to also do, though, is to have ratios that are not positive. So if I build a crooked coordinate plane here, and we draw an angle in standard position such that the terminal side is in quadrant 2, and our angle theta would be some number of degrees or radians here. And let's say this terminal side goes through some point now x comma y. Well, this time our x-coordinate will be negative because we're in quadrant 2, and our y-coordinate will be positive. Again, we can drop our altitude to the x-axis, and that provides us a hypotenuse, an adjacent that is equal to our x-coordinate, and a opposite, which is equal to our y-coordinate. And because our opposite would be considered positive in the positive y direction, and our adjacent is negative, well, this means that our sine of theta, the ratio opposite over hypotenuse, is still positive. Cosine of theta, however, our x, or our adjacent, is negative. So negative over positive gives us negative, and tangent of theta also produces a negative. So in our expanded understanding of trigonometry that we're building on the coordinate plane, we can have positive and negative ratios. Our reference angle, remember, this is our reference angle, sort of the angle inside the triangle that we build, but the actual angle that we're doing calculations on is the angle in standard position. Okay, but a really key idea here is that the opposite side here and here end up just being the y-coordinate. So opposite really just ends up being the y-coordinate based on how we're building our triangles. And then similarly, the adjacent side, based on how we build the triangles, the adjacent ends up corresponding directly to our x-coordinate. And that's a really important idea, and I want you to keep that in mind as we proceed forward. Building off that idea, if we consider our ratios, because our trig functions produce ratios, that's very important. Our sine ratio of theta, which is equal to the opposite over the hypotenuse, but we said our opposite is just our y-coordinate, so it's actually equal to y over the hypotenuse. Our cosine ratio, cosine of some angle theta, is equal to x over the hypotenuse, because x is always our adjacent. X-coordinate corresponds to the adjacent. And then tan of theta is equal to the y-coordinate, the opposite, over the x-coordinate, the adjacent. And there's something really nice about tan of theta. We are completely dealing with our coordinate points. So tan of theta, we can just express using the ratio of our y and our x-coordinate. Sine of theta, we are almost there. We have the y. In cosine of theta, we have the x, but we still have to think about this hypotenuse. So we'd still have to know the hypotenuse, which in theory, maybe we'd have to use the distance formula, or Pythag to calculate the length of the hypotenuse. And so the question I'm going to pose to you is, how can we make this system easier? And often easier is synonymous here with more powerful. Okay, how can we make this easier and more powerful? Because right now, if I wanted tan of theta, I can just look at my x and y coordinate and get it. If I want sine, I can look at the y, cosine, I can look at the x, but we still have this hypotenuse. So the question is, what would the ideal hypotenuse be? What would we really like it to be? And let's recall something about similarity. So if I build a grid, coordinate plane, and let's say I have a point in quadrant 1, and let's use the point 3, 4, just for simplicity's sake. And I know that a 3, 4, 5 triangle is going to make a hypotenuse of 5, an opposite of 4, and an adjacent of 3 for some angle theta if we build out our angle in standard position. But the interesting thing here, and actually I'm going to do that in a better color, blue, same color, thinner lines. If I build this angle in standard position here and call this angle theta, if I instead had used the coordinates 6, 8, well, by similarity, I actually end up with the same ratio. 6, 8, that would make my hypotenuse 10, my y-coordinate 8, my x-coordinate 6. And so regardless of which triangle I use, I could use this big red triangle or the smaller black triangle here, I would get the same ratio. So sine of theta I could say is 4 over 5, or I could say it's 8 over 10, but at the end of the day, like, those are the same thing. It doesn't matter which triangle I use. So if I can use any triangle, and I'm asking the question how to make it easier and more powerful, how do I sort of get this hypotenuse thing out of there so I can just use the x and y coordinates? What would the ideal hypotenuse be? Well, the answer is the ideal hypotenuse would be 1. The ideal hypotenuse for doing trig is 1. And this is really important. So if I have my trig functions, and say I have sine of theta is equal to the opposite over the hypotenuse, but we said the opposite corresponds to the y-coordinate. Now our hypotenuse is 1, so y over 1 is just y. So our trig function sine of theta corresponds exactly to the y-coordinate, so long as the hypotenuse is 1. So sine of theta is just the y-coordinate, if that hypotenuse is 1. Cosine of theta, then, would be the adjacent, the x, over the hypotenuse, 1, or just be the x-coordinate. And then tangent of theta hasn't really changed much because we didn't need the hypotenuse in the first place. But now we are able to relate the trig function directly to the coordinate. There's no other stuff that needs to happen. And that is a really, really important, dare I say, magical idea. Magical. Okay. But if we want this hypotenuse to be 1, we must ask ourselves, what is the set of all points that will have a hypotenuse of 1? I'm going to pause and write this so you can think about it. What is the set of all points that will have a hypotenuse of 1? And recall that we're talking about the hypotenuse as being the distance from the coordinate to the origin, is distance to the origin. And so if that's the case, well, then this must be a circle with radius 1 centered at the origin. A circle with radius 1 centered at the origin. This is the set of all points that has this hypotenuse of 1. And this is the unit circle. This is our super powerful tool. It is a circle with radius 1 centered at the origin. Okay, so let's take a look at our unit circle and see why it's so valuable in our study of trigonometry. So if I build out my axes again, and I plot some points, I know that the coordinate 1, 0 must be on this circle. I know that 0, 1, -1, 0, and 0, -1. And then if I attempt to draw a circle, perhaps the computer will help me, or perhaps not. Let's try again. Did not think I was very close to a circle, huh? There we go. Okay, so here's my unit circle. And so any point, if I go ahead, let's go purple, I put some point here, x, y, I'm guaranteed to have a hypotenuse of 1. If I put some other coordinate here, x, y, I'm guaranteed to be a distance of 1, right? No matter where I go, I'm always going to be 1 away from the origin. And what's so valuable about that is if those are my x and y coordinates, and I think about my definition of trigonometry and drop my right angle, and here's theta to this angle in standard position, well then, for this point that lies on the circle, and I'm going to say if a point lies on the unit circle, then it must be true that sine of theta is simply equal to the ratio of the opposite to hypotenuse, which is equal to y over 1, which is equal to y. So sine of theta equals y if a point lies on the unit circle. Very important. And then similarly, cosine of theta would be equal to x, and so on. What's so important about that is this y, this is the sine ratio. That y coordinate, that right there, represents the sine ratio for this angle. And say I had instead picked a point on this same angle, right? Say I picked a point way out here, such that this point was given by 2x and 2y. Well, that would make my hypotenuse 2, because x and y gives me a hypotenuse of 1, so we must be scaling up by a factor of 2. Hypotenuse doubles. This would make my y length, or my opposite, 2y, and my x 2x. And thus I would say that sine of theta is equal to 2y over 2, which is just equal to y. So it actually doesn't matter so much that, or I shouldn't say that, but the important thing is this y is the sine ratio. And it doesn't matter if we're imagining a big triangle or a small triangle, this y coordinate, the y coordinate such that the point is on the unit circle, is the ratio. So if the point's on the unit circle, then the y coordinate is the sine ratio. If a point's on the unit circle, then the x coordinate is the cosine ratio. And that is super, super, super powerful. Okay, that is the main idea. That is what we want to take away from this. I'm going to do 1 or 2 examples now, just to sort of show you and get you a little bit more familiar, but that's the main concept. So let's take a look here, and I'm going to say, let's go like this. And I'm going to build another unit circle. I'll assume this is good enough. Good job. And let's say I know that the terminal side, say I know the terminal side of the angle 5 pi over 6 goes through the unit circle at the point -√3 over 2, 1/2. Now, how do I know that? Well, you'll learn that very soon, and you will know that very soon too. But regardless, say I have this angle, so let me draw an angle in standard position, 5 pi over 6, or 150 degrees, so we're somewhere around here. And here's my angle, 5 pi over 6, and say I know that we go through the coordinate -√3 over 2, 1/2. Based on what we just talked about, I can immediately say that that x and y coordinate are my sine and cosine ratios. But let's go through the process to see. So if I draw my triangle the way I've been doing, and I have my reference angle, and I have my hypotenuse, which must be 1 because we're on the unit circle. My opposite is 1/2, and my adjacent is negative square root 3 over 2. Then it should follow that sine of theta is equal to the opposite, 1/2, over the hypotenuse, which is 1. But anything divided by 1 is itself. So sine of theta is 1/2. Sine of theta is 1/2. And when I say theta, I guess I should be saying that sine of 5 pi over 6 is 1/2. What do you think cosine of 5 pi over 6 is going to be? Well, we should be able to know right away from this information. But to see it out doing it the long way, we know that it's the adjacent square root of 3 over 2 over the hypotenuse of 1, but anything divided by 1 is just itself, and that's the power of this hypotenuse of 1. Cosine of 5 pi of 6 is negative root 3 over 2. So this unit circle literally has every cosine and sine ratio built into it. Like any point I can pick here, x comma y, and say I imagine some angle theta, well then sine of theta is y, cosine of theta is x. And that's really, really powerful at the very least, and cool. It's cool to be able to build something like this. So I'm going to do one more example of that. Let's build out here. Maybe let's put us in quadrant 4. So let's say I have, I want to do the trig function. So say I know that the angle of, let's do a negative angle, negative pi over 4 intersects the unit circle at negative square root 2 over 2, positive square root of 2 over 2, comma, negative square root 2 over 2. Okay, and say I want to determine the cosine and the sine of theta. Well, let's draw our unit circle, more or less. And let me draw my angle in standard position with my initial side and my terminal side. Because my angle is negative, that means I'm going regular clockwise. So that's my angle of negative pi over 4. And I know that there's this coordinate of square root 2 over 2, my x, and negative square root 2 over 2 is my y. Well, this means that I know that sine of negative pi over 4 must equal negative root 2 over 2. I know that cosine of negative pi over 4 must equal root 2 over 2. Now say I wanted to keep going and do more of the trig functions. I could do tangent, which is going to be equal to the y-coordinate, the opposite, over the x-coordinate, the adjacent. So it's going to be negative root 2 over 2 divided by root 2 over 2, which is just going to be negative 1. Something divided by itself is always 1, or negative, if one's negative and one's positive. So that is the beginnings of the unit circle. That is the main idea behind it. We'll cover this more and look at more applications soon, but hopefully this was useful, and thank you for watching.